late 16th century, the 1590s.
Should we not be writing this down?
This part you don't have to write down, but there was a man named John Napier. And John Napier was a lunatic. John Napier got his neighbor's pigeons drunk. This is the guy I may have told you about before, where his neighbor's pigeons kept flying over and eating out of his garden, and his neighbor denied it. So he said, finally one day he took the seeds he was going to put in his garden, and he soaked them in alcohol first. And he planted them. Doesn't really help the plants grow better, but when the neighbor's pigeons, domestic pigeons, flew by and ate out of the garden, the pigeons all got drunk and took a little nap in the yard.
Wait, does that really work?
Apparently.
Oh, that's so cute.
So the neighbor comes running down from his estate next door, and the neighbor says, "What have you done with my pigeons, you jerk?" And John Napier said, "Oh, you mean the pigeons that you swear never come to my yard? They're out sleeping off their hangovers in my back 40 acres. What? I don't know if he said that last part. But he should have. John Napier was the kind of guy who thought that way, and that's the kind of man who would wake up one morning and quite literally, apparently from nowhere, ask, what if exponents worked backwards?
What?
John Napier may be the smartest mathematician in history. If you look at what Einstein did, you can see the work upon he was. That's true. If you look at what Einstein did, you can see the work he was building upon other people. Even Rene Descartes, my favorite, was actually stealing from a few other people. And Isaac Newton flat out said, "If I have seen farther than others, it is because I was standing upon the shoulders of giants," referring to the mathematicians who came before him. No one can find any evidence that anyone in human history anywhere was thinking about logarithms until Napier just started writing about them one day. It may be the single most original idea in math since people decided to start counting on their fingers and toes. And here's what he came up with.
I want to kill him.
That's right. This is the man you have to go back in time and stop. Because it may be that no one else ever would have come up with them. Probably not. If I have the statement 5 squared equals 25. First, Napier came up with a notation logarithm from the term logical algorithm.
When should we start writing stuff down?
Now's a good time. Logical algorithm, I actually want you to know. Logical, you know what it means. Algorithm is a method of solving a problem or a flowchart. Algorithms are used in computer programming. It's basically a method to accomplish something. First, as you guys should know by now, I can rearrange this statement, and I can say it's log base 5 of 25, and it's equal to 2. A logarithm is always a question. The answer to that question is always?
The exponent.
The exponent. It's always the exponent. The properties of logarithms he came up with are actually left over from Mr. Singer's class earlier today. One of them, I'll rewrite them from up there actually. The top one is if you have the log base b of a times c, you can expand the logarithm into the log base b plus the log base b of c. This is analogous to if you have...
What? Analogous? Oh.
If you have b raised to the a times c power, you can change it to b to the a. Hang on, I'm writing this wrong. If you have b raised to the a plus c power, that's the same as b to the a power times b to the c power. Addition inside the exponents in algebra becomes addition between the exponents in logarithms. Remember, each logarithm is an exponent. So if you can add exponents down here, you can add exponents up here. That's the first property.
Wait. Okay, no, I don't get it.
The next property is...
Where's your water bottle?
If you have... Do you have the water bottle, Albert? Locker. You can make it, Ramsey. I have faith in you. Is if you have the log base b of a over c. What does this change into?
A log of a over a minus, yeah.
Log base b of a minus the log base b of c. Okay? And my favorite, which I went over a bit last time, The clog, is that what Mr. Singer calls it?
Or the swoosh, as you call it.
The whoosh, I like whooshing. If you have the log base b of a and you raise it to the c power, this becomes c times the log base b of a. An exponent becomes a coefficient.
Why?
This one I can actually explain most easily. This one you can see as an analogy to
That one.
division, yeah.
Yeah.
But this one, this is actually fairly easy to prove by example anyway. Let me erase John Napier's name.
You don't need to prove it. I'm okay with remembering that rule.
I'll give you an example though. If you have the log base 5 of 3 to the 4th power, okay? May I rewrite this?
It's 4 times.
Yep, as log base 5 of 3 times 3 times 3 times 3. Is that allowed?
Yep.
Then by this property, it is the log base 5 of 3 plus the log base 5 of 3 plus the log base 5 of 3 plus, once again, the log base 5 of 3.
Crap, I get it.
1, 2, 3, 4. So if I can spread it out into 4 different logarithms and add them up, that's the same as 4 times 1 log base 5 of 3.
So you use that rule to get the swoosh thing.
Yep, to get the whooshing down of the exponent
Swoosh.
to the swooshing down of the exponent to the coefficient. Okay, these are the 3 big properties of logarithms. They lead to some very powerful things. Yes.
Is that the same as log base 5 of 81?
Yes, it is. This is also the same as log base 5 of 81. Is that really helping the picture?
No, I just
draining my battery.
thought I'd piss you
All
off.
right. Yes, thank you. May I erase this property down here?
What were you doing, Ramsey? Yeah.
Turn on the flash.
You can use it like a spotlight feature while you're videoing. Okay. Here's my favorite use of these rules. Expanding and condensing, I know you guys did last year. Historically, this was powerful. Doesn't look like it, but in the 1590s, this was the Pentium computer chip of its time. This knowledge.
No, we're now at core i7.
This was the quad core. Yeah, we are. We're now at i7 quad cores, and you can put up to 4 of them in a
Yeah.
high-end Mac. So this was really the equivalent.
Pentium.
Yeah, Pentium.
What the hell?
To Nick and
Heck.
Alba, you asked me a minute ago.
Phones are getting dual core processing.
Yeah, I know.
It's insane. The latest iPad has it, doesn't it?
The Droid Bionic, which should be coming out soon, has it.
Wow. My phone's fast, and I'm getting old if I say my phone's fast enough. You should always want the fastest. That's how you know you're staying young.
It's also how you get broke.
Hey Nick, segueing from your question, and now about 15 minutes ago. 5 to the x equals 25. What's x? 2. How'd you know?
Because he found the log.
That's 5.
5, right. 5 times 5 is 25. Maybe even had it memorized at this point in your math career. Okay? 5 to the... What's x now?
The log of
Isn't that annoying? I mean, it's a little more than 2, right?
0.
log base.
That'd be an excellent guess.
It's a log base 26 of 5 or something.
Excellent. You can rearrange the logarithm. There's actually a bunch of different ways to think about this. If you just rearrange this into a logarithmic statement, the base remains the base of the logarithm. What the exponential statement equals goes inside the log, and a log always asks a question, and the answer is always the exponent.
But then we still don't know anything. We just
Well, now we can type it in a calculator.
True. We don't.
We still don't know.
There's another way to do this. Another way to look at this that we also won't know anything at the end of. But I'll show it to you anyway.
So how do we figure this out?
I'm going to take the log base 10 of both sides of this equation.
It's the opposite of 2ing it.
Okay? I'm going to take the log base 10 of both sides. I'm going to whoosh down the x so that this becomes x times the log base 10 of 5 equals the log base 10 of 26. Okay? You guys with me so far?
Yeah,
Is all
and then
that
you're going
allowed?
to divide?
Now I'm going to divide both sides by this number. Remember, this is just a number. It's 10 to what power equals 5. It's going to be some fraction.
Wait, you're allowed to change log 526 to log 5 to the x powers?
Yes, there's something you can do there. In fact, we've sort of already done it. So here are my two answers. Are either one particularly helpful?
No.
No. Okay. I'm going to get you a helmet cam someday, Ramsey. But you get the idea how they're the same thing.
Yes.
Okay. Good, because that's what's called the change of base rule.
Randy, that's gonna be really annoying for the person that's trying to watch the video.
Yeah.
It's only Megan,
Okay,
guys.
Stop. Be nice with it. Okay, now, what
And
this
who?
tells me is
crap.
that
Sorry, Kathleen.
the log base 5 of 26 must be equal to the log of 26, which I suddenly can't write, the log base 10 of 26 over the log base 10 of 5. What would happen if I'd taken the natural log of both sides?
It'd be the same.
I would have wound up with the natural log of 26 over the natural log of 5. What would have happened if I'd taken the log base pi of both sides?
Be the same,
It'd
except
be the same.
with a
It'd be the
different
log base pi of 26 over the log base pi of 5.
that sucks.
This is what's called the change of base rule. What's called the change of base rule? The change of base rule is if you have the log base anything, the log base a of b, you can rewrite it as the log base 10 of b over the log base 10 of a. You may also write it as the natural log of b over the natural log of a. What buttons does your calculator have?
Log base 10 only.
Log base 10 and
And
there's
the
also a natural log button.
yeah.
It doesn't have a natural log of 5 button on it anywhere, does it?
There is a way to do it.
This is the way.
I thought there was an actual way to plug in log base.
Oh, you know, there may be under the
but
command menu, but I don't know
tough,
it.
yeah.
Okay, the easiest way on your calculator to do this. If I ask you what the log base 5 of 26 is, you will find the log base 10 of 26 and divide it by the log base 10 of 5. Or you'll find the natural log of 26 and divide it by the natural log of 5. Either way, you'll get 2.0 something. Yes, sir?
Do I sense we're going to have a calculator on the next test?
For at least these questions. For at least these questions.
You
won't have it on
suck.
graphing the logarithms, but... Okay, come on back over here.
Why not?
So that's a how-to. Now let me get back to Napier's time again, the 1590s, the pre-calculator days.
Is you laughing at me?
I do. He's a trip. He's a trippy character. John Napier. I can't relate to him at all historically, but he was an interesting guy. All of a sudden, though, for the first time, you had an analytic method for solving problems like this. Now, what Napier then devoted many years of his life to was creating sets of tables.
Was he married?
Ooh, that's a great question.
Was she-
It really, I mean, they do seem to be into two categories. There used to be a lot of these guys who were like reclusive freaks, yeah.
And some
Some
were
of
just...
the-
Wait, what's the other category?
Some of the smartest ones were like the two
Like,
people
what's
who
his
were,
face? They didn't really try, but was just a genius in his spare time.
yes, like Fermat supposedly had a perfectly normal life. Yeah, exactly. Rene Descartes was supposedly, I mean, he had a girlfriend, he had a life. The two guys who were credited with inventing calculus, Isaac Newton and
The
Wilhelm
German
Gottfried
dude.
Leibniz.
Yeah.
Wilhelm Gottfried Leibniz supposedly was a party animal, went out, had fun, went to dinner all the time, married kids. Isaac
Married
Newton
kids.
he was married and he had kids, I think. Isaac Newton was more the stereotypical mad scientist type, reclusive, never talked to anyone.
Loser.
He, I mean, some people look at his biography and say he was possibly autistic, but
What? Would you run stuff
Well, he
through
was on
like
a lot of
through
Reading
your
books on my
history?
own.
Oh.
just, yeah, I'm reading a lot of my own. Okay, getting back to this problem. What would happen on this problem is you would get to the point where you realized x was the log base 10 of 26 over the log base 10 of 5, and then you would go to Napier's tables. And Napier's tables would tell you what the log base 10 of 26 was and what the log base 10 of 5 was. So these rules in those tables, all of a sudden many calculations became very different. Okay, very, very different. Quick example of how this might have worked historically. And this will not help you as directly on the homework, but if you really pay attention to the concept, it will help you on the homework. So I'm intentionally making you have to think a little bit more
Wait,
about
the homework's
this.
still graphing?
No, the homework's not is just manipulating logarithms.
Oh,
Spello?
Yeah.
What if it was 5 to the x squared equals 25?
Then you'd have x squared equals log base 26 over log base 10 of 5.
No, but if it's 25.
So 5 to the that,
X squared? Oh.
5 to the x.
What was the point of that?
then it's going to be the square root of x equals that.
Is maniacal.
Yeah, I mean, then x would be that. Is one way to look at it.
That's not fun.
But you could also, since this is x squared, it's x.
Times
What
x.
do you do with a power times raised to another power?
Add them.
Yeah.
Oh, wait.
You multiply
no,
them.
Yeah, you multiply.
Oh,
So this is 5 to the
Would it just be
x
4?
to the x. You could do that. There are things you could do, but this
You
would
could do
be
stuff.
where you'd be stuck. But let's not get too far into that yet. There is a question like that will come up in calculus. Okay, here's an example.
Why is there one question like that you know?
What if you needed to know the cube root of 880 to solve a heavenly body problem, where the stars were? It was of great interest to guys in Napier.
Guess and check.
I mean, but seriously, where would you know where to start to find the one number that multiplied by itself
Well,
3
it's
times?
probably
Calculator.
10.
You'd
Without
find
a
the
calculator.
third root of 88 first. That's what I would
It doesn't. It's not
Is it-
linear. It doesn't help
is
you
it 8?
directly.
I do.
No,
Is it
I know it's between.
Am I close?
I know it's less than 10 because it's
It's 9. 81.
yeah, it's close. But you'd be guessing and checking, basically. If you needed more precision than that.
9 times 9 times 9 is 729, and
Okay, so
10 times 10 times 10 is 1,000.
so you know it's in between 9 and 10.
Wait, but this is an actual.
No, but it's
Oh.
But here's a new trick you had, thanks to Napier. If you had his table, if I take the log base 10 of both sides, well, first off, I'm going to rewrite this as 880 to the 1/3 power. Okay. Now I take the log base 10 of both sides, and it's to the 1/3 power, right? Now I swoosh down my 1/3. Okay. And now, I use my property of logarithms to switch this to log 8 plus log 11 plus log 10. Where did I get those three numbers from?
You divided 880 by its factors.
Into its factors. Very well said. Yeah. 8 times 11 is 88, times another 10 is 880. Now all I need is a table of logarithms that goes up to 11, and I can find the log base 10 of 8, the log base 10 of 11. What's the log base 10 of 10?
1.
1. So this is 1/3 log base 10 of 8 plus log base 10 of 11 plus 1.
Oh my god, I got 879.
Really?
So close.
8.79?
No, 879.
Oh, by guessing and checking?
Yeah, it's 9.58. I just do 879.
Okay.
Two.
Good guessing and checking. Just out of curiosity, what's the log of 8? Alba? Get used to finding where the log button is.
0.903.
Okay, so that's 1/3 times 0.903. What's the log of 11? Should be 1 point something, so it's just a little more than 10.
Well, do you want to add those?
No, just give them to me separately first. Thank you.
1.04.
1.04 plus 1. Okay, so what's 0.903 plus 1.04 plus 1
And divided by 3.
divided by 3?
That's 1.9. No, sorry. 2.92.
Then divide that by 3.
Yeah.
No, because that doesn't sound right. Does it?
Yeah. 2.9? No way.
No, yeah, that can't,
No,
yeah.
it's
Oh,
0.908. 01.
What is it?
0.901.
Yeah, 0.901. Okay, so 0.901, now this is not equal to x, this is not equal to the cube root of
It
880.
equals the log of x.
How
This
is
adds up
point-
to about 3.
You divided it already.
Yeah, divided already, yeah. Now this adds up to the log base 10
So 10 to the 0.901th power
is the cube root of 880. And maybe for now you can either figure this out, or maybe from your calculations it's easier to leave it like this. But what we just did, and you guys had calculators to help you, and as painstaking as it was so much faster than any other method of finding this cube root before.
Alba did it faster than us.
That's right, before Napier invented logarithms. That's why, seriously, this was like dropping a TI-83 back in time. I mean, mathematicians who got a hold of these tables could suddenly do twice as much work in their working life. He actually, one of the quotes about this was, Napier has doubled the working life of every living mathematician. What they could now accomplish, what they used to only accomplish in 20 years, they can now accomplish in 10. That's how powerful these things were.
It's like that new commercial with that phone with the 2 touchpads saying make it just as famous, like as fast.
You know, it actually is. That was one of the that could have been great advertising for Napier's tables.
I'm guessing he made people pay for this stuff.
He was actually a rich Scottish lord in a time of what's called noblesse oblige, where the nobility felt obligated to help those out. I think he actually just started handing them out and just wanted the prestige. I believe it was open source, in other words. Actually, not proprietary. But, you know, what do you expect from the guy who got his neighbor's pigeons drunk?
Could have made band.
Can I go to my locker?
Yeah.
Of course you would be.
I hope you find it, Jeanette.
Got a business on someone. And I'm Jewish.
Can I turn this off?
Not yet, not yet. Okay, how do these properties play out in other ways?
They don't.
They do. They really do.
His head is so shiny. What?
You also said they don't?
Yes.
Okay, for this example, what I want you to do is expand as far as you can and answer it if you can.
Can we use a calculator?
Simplify as far as possible. So, the log base 4 of the square root of x over 64. What can we do first of all?
Square both top and bottom?
Yeah.
No, you can't do that with a fraction. You can square both sides of an equation, but inside it you can't. Besides, I don't want to deal with 64 squared. If you see division inside a logarithm,
You can subtract.
Janine found her phone. The world can sleep more easily tonight.
So it's log base 4
So guys, did you guys hear what Ramsey said?
root x minus.
Guys, if you see division inside a logarithm, you should immediately start thinking subtraction between the things being divided. Now, here's the next thing. If you see a radical inside a logarithm, what should you change it to?
The square root of square of 1/2
Oh,
to the 1/2 power.
To the 1/2 power, a fractional exponent.
If you can solve log base 4 to the 64th, can you just solve it like that?
You must, in fact. What is log base 4 of 64?
4 or yes, 8 2 2.
3, thank you.
I don't know.
Stressful.
4 to the 3rd power is 64. 4 to the 3rd power is 64. A logarithm is not fully expanded if it still has an exponent you can bring down.
I like this because it's like algebra.
It is algebra.
Yes.
So this 1/2 has to come down to the front, and I believe that's a good place to stop. I don't think we can get x anymore by itself.
Well, you can add 3 to both sides and then multiply it by 2.
There aren't both sides. This wasn't an equation, it was an expression. We've just been manipulating one side.
No, but they're equal to
It's
each
only
other.
equal to what we started
Yeah,
with.
you're
We
right.
started with an expression. And it is then equal to this expression, this expression, and this expression.
This stuff is awesome.
Equal sign.
Yeah, it's really just puzzle manipulation at this point. You gotta know your...
Shiny head.
Okay, the change of base rule we went over. Use condense and express. Let's do condensing some real quick. Okay, where's one that... Alright, here's one. Alright, 61. The 3 natural log of x plus 5 natural log of y minus 6 natural log of z. Okay, when you're condensing, so 61, which you're only have even on the homework, so you won't do, but this
Can't
is
you take the factors and put them as squares?
the coefficients and put them as exponents. Yes, I understood what you meant. We're in your vocabulary a little. Okay, this is important though, guys. You cannot condense logarithms if you have coefficients. But luckily, as Ramsey said in his own Mad Lib sort of way, you can take coefficients and turn them into exponents. All these rules work forward and backwards. And now, anywhere you have addition, you can change it to multiplication of what's inside the logarithm, and subtraction becomes division inside the logarithm. So this is now the natural log of x cubed y to the 5th over z to the 6th. You cannot condense with coefficients. You got to get rid of them first. How many of these rules work if we have different bases?
None.
None. None, none, none. None
Unless
at
you
all.
change the base.
None.
Unless you change the base.
None.
That can actually be exciting.
Then one of them works and then they all work.
That can be,
That's...
that can sometimes be helpful.
Well,
Sometimes.
then let's start changing some bases.
For some reason I'm thinking, did we get to the equations yet? No, this is all just expressions. It's expanding. Okay, hold on one sec.
One sec.
A lot of these are easy. That one's going to be exciting. Use a calculator for some, no calculator for others. Okay, I'm going to let you guys start, and I do mean start, on page 421, 4 through 80, every fourth. And just because we haven't had enough attention spent in class today on this, I do mean for the next 11 minutes, no one's doing anything except these problems. Get going.
Say goodbye.
Goodbye.